Hello, I am Seung Sang Yoon from Seoul National University in South Korea. And my advisor is Professor Ayan Kim. And today I will discuss our paper, tightly coupled multi-RGBD inertial odometry, which employs front and rear RGBD camera and inertial configuration to estimate the pose in the featureless environment such as construction site. As many people know, mobile robots play the important role at construction site. Firstly, precise navigation. Odometry and mapping enable robots to navigate indoor construction site which has no GPS signal, avoiding obstacles and reaching destination safely. And mapping result can aid efficient resource management. For example, offering 3D information of material, equipment, and personal location so it can boost productivity. About other cases, it can continuously monitor the progress of construction, and sometimes it can secure the workers safe as well. These reasons may be why we conduct robot research in difficult environments such as construction site. But there are a lot of obstacles to estimate the robot's pose in construction site. First, lack of distinct features. The absence of clear visual features make it challenging for mobile robot to navigate and map indoor construction site. And construction site include a lot of dynamic objects. So it is easy to failure if dynamic object make occlusion. And sometimes the variation of lighting condition cause tracking failure. To overcome these challenges, we propose a multi-camera solution using a front and rear configuration on mobile robots. This setup enhances tracking accuracy by providing complementary data from different perspectives. These are our contribution. We've developed a method that tightly integrates both front and rear RGBD camera, improving odometry accuracy by leveraging complementary information from multiple perspectives. And our approach incorporates a point selection metric that considers the motion dynamics of the robot. It can enhance the convexity of optimized residuals. Third one is depth refinement process. Unlike existing methods that only use points where the depth camera's measurements are valid, we select valid points for odometry and project them onto the depth image to determine if they are valid point or not in consecutive frames. And the point is activated in odometry framework. Details will be addressed in later slide. These are our systems overview. Contribution points are highlighted with blue color. In initialization phase, we start by establishing a world coordinate system aligned with the gravity direction using IMU measurements. Then we activate the initial points and estimate the initial pose utilizing points which has valid depth values for enhanced accuracy. Then in the tracking and depth refinement module, we configure residual and compute a coarse pose relative to the latest keyframe. Then we detect point correspondences between frames and adjust depth values to ensure precise state estimation in this phase. Finally, in the backend optimization phase, we refine pose, point depth value, and IMU biases using sliding window approach. This slide is about the motion-guided point selection metric that enhances our odometry system's performance. In direct-based approach, the difference of pixel intensity configure the optimized residuals. So we thought about which point to choose to construct the optimal residual for calculating the robot's pose. For example, first figure, A convex residuer will be configured in yaw direction of the robot. In the case of second figure in the middle, it does not affect the yaw direction. In the third case, it will construct a residuer, convex residuer in lower pitch yaw or direction. Consider, I'm sorry. Considering these facts, direction of the gradient associated with the convergence of the residuer and the size of gradient associated with the stiffness of the residuer. So we tried to select the points which has same gradient direction with the robot motion. The existing method selects point with a gradient size above a certain level to have a uniform gradient direction throughout the dot product with the randomly selected direction vector like the figure on the left side. In that case, if the effective to robot motion point is absent, tracking loss may be occurred. However, we reduced the spacing of the direction vectors and calculated the parallax vector of the match point between consecutive frames. The direction vector was adaptively rotated by the angle of the corresponding parallax vector, and the points which have the maximum gradient inner product value with that parallax vector will be selected. Therefore, points that can contribute to the convex residuer of the robot's motion is selected. This slide is about the method to efficiently manage points used in odometry framework. As shown in the figure above, RGBD cameras have limitations in their measurement range, and there are many points with invalid depth values. The existing method use only points with valid depth values, so distant points outside from the depth camera measurement are not used for the odometry. Because distant points could be valid for odometry pipeline, we used the following method. The point is projected onto the depth image and has a valid depth value, or point which has good matching quality are utilized in the odometry pipeline. By incorporating these criteria into our odometry, our depth refinement process, we ensure that our odometry system can effectively utilize valuable points for accurate state estimation. This slide is about the tracking and backend optimization module. We modified the Jacobian associated with rear camera residuer to align with the front camera, ensuring the pose estimation consistency. In the backend optimization stage, pose point, depth values, and IMU biases are refined using a sliding window. These are our results. The ground truth derived from LiDAR SLAM, a 34-meter distance data was used for testing. The point cloud with red color is from the front camera, and blue color, point cloud with blue color is from the rear camera. And we compared with Vince Mono and Warby Slam 3 RGBD IME version, one of the state-of-the-art of the odometry system. Our system outperformed the comparison group, showing superior result compared to our method using only the front mono camera case. That's all. Thanks for listening my presentation. And this work is collaboration with Hyundai Motors. And if you have any questions, please feel free to contact us. Additionally, there will be a presentation on Thursday regarding RGBD multi-camera extrinsic calibration in conditions with limited field of view. We kindly request your attention. Thank you again.